Welcome back to Above and Beyond, where space is never silent and neither are we. I'm Roosh.
And I'm Rock. Today we're diving into the violent, beautiful chaos of asteroids, the rocky relics that helped build the solar system and nearly tore it apart.
We'll break down how asteroid impacts shape the structure of planets, why the late heavy bombardment is still debated in labs today, and how shockwaves from these collisions can literally melt rocks, tear planets open, and even vaporize crust.
And at the end, we'll show all this ancient violence has very real consequences for us here on Earth, because the space rocks are still out there.
What even is an asteroid? Asteroids are essentially planetary leftovers, fragments of early solar system material that never coalesced into planets. Most orbit in the asteroid belt between Mars and Jupiter, where Jupiter's gravity prevented a planet from forming.
They range in size from a few meters to nearly 1,000 kilometers, like Ceres. But their importance isn't in size, it's what they have done. Because as small as many are, when they hit something, they punch far above their weight class.
The solar system's scar tissue, the late heavy bombardment. Let's talk about the late heavy bombardment, or LHB. Around 4.1 to 3.8 billion years ago, the inner solar system went through a violent storm of asteroid impacts. You can still see the scars, giant basins on the moon, craters on Mercury, and even hints on Earth's crust.
The LHB wasn't just a random shower of rocks. It may have been caused by gravitational reshuffling of giant planets. One theory, called the NICE model, suggests Jupiter and Saturn drifted into a resonance, meaning their orbits aligned in a way that destabilized the Kuiper belt and asteroid belt. Millions of bodies were flung inward.
Imagine entire asteroid families slingshotted toward the sun, some crashing into planets, others ejected entirely. These weren't just peppering the surfaces, they were carving out multi-hundred-kilometer basins, vaporizing oceans, and boiling atmospheres.
Earth likely got hammered too, but our active geology erased most of the craters. What we do have are ancient zircon crystals that show sudden spikes in pressure and heat, geochemical footprints of enormous impact.
How asteroids shape planets. Literally. Here's what makes asteroid impact so unique. When one hits a planetary surface, the energy is not just mechanical, it's thermodynamic. A typical asteroid impacts at velocities of 15 to 25 kilometers per second. That's like compressing the kinetic energy of a small nuclear arsenal into one strike.
That speed doesn't just leave a dent. It generates shockwaves that propagate through their crust. At the point of contact, pressures can exceed 100 gigapascals, more than the pressure at Earth's core.
This leads to what is called shock melting. Rock doesn't just fracture, it transitions into a plasma-like state before re-solidifying. Silicates liquefy. Metals vaporize. You get a transient crater, sometimes 10 to 20 times larger than the impacting body.
And don't forget about the isobaric core, the central region where pressures are relatively uniform. It's a zone of maximum thermodynamic chaos, rock flow, melting, and possibly the creation of high-pressured minerals like calcite or stisovite. Outside the isobaric core, material experiences spallation, a tensile fracture process. Basically, as the shockwave reflects off the surface, it rips rocks apart, launching fragments at escape velocities. This is how Earth rocks end up on the moon, or how Martian meteorites make it here. Then the whole crater begins to collapse. For large impacts, the rebound of the crust can push up a central peak. Think Tycho crater on the moon. Material from dozens of kilometers deep can be brought up to the surface. That's why impacts are a window into planetary interiors.
Shock physics, a deep dive. Let's pause and go full throttle on impact physics. The first wave, produced in a hypervelocity impact, is the shock wave, which compresses material instantly, raising both pressure and temperature faster than any volcano or tectonic force. Following that is a release wave, which decompresses the material. If the release is fast enough, it causes fragmentation. This is what generates the highly shocked bacases and melt rocks you find in impact structures. Crater formation has three phases. First, contact and compression, where the energy is transferred to the surface. Then excavation, where the shock waves expands radially and lifts the crust.
Modification, when the unstable cavity collapses under gravity.
The peak shock pressures in the contact phase are mapped using Houganian curves, graphs that relate shock velocity to particle velocity. For granite, peak pressure can exceed 50 gigapascals in milliseconds.
At those pressures, even quartz, one of the most stable minerals, transforms. You see planar deformation features, microscopic lamellae and crystals. It's how scientists confirm ancient craters, even if erosion has flattened them.
Some of the rock vaporizes into a superheated gas that rises above the surface, forming an impact plume. This can inject dust into the atmosphere or eject material entirely into space.
The really big ones, they cause global effects. Debris rains down, skies darken, and photosynthesis dies off. The Chicxulub impact 66 million years ago may have caused months of global winter. Asteroids as time capsules of solar system formation. Now here's the cosmic twist. Beyond their destructive power, asteroids are also among the most important witnesses to solar system history. Think of them as geological time capsules that preserve the original ingredients from 4.6 billion years ago.
Unlike planets, which underwent heating, differentiation, and tectonic cycling, most asteroids are chemically primitive. Many have never melted. Their composition, rich in silicates, carbon compounds, and sometimes even pre-solar grains, let us reconstruct the solar nebula conditions before planets existed.
And we don't need to guess. By analyzing the isotopic ratios of meteorites, chunks of asteroids that land on Earth, we can track the timing of planetary formation events. For example, calcium-aluminum-rich inclusions, CAIs, and carbonaceous chondrites are the oldest solids in the solar system. Their lead isotope dating gives us a formation age of about 4.567 billion years.
We even use different isotopes like aluminum-26 or hafnium-tungsten systems to date core formation in planetesimals. So by comparing asteroid samples, we can tell when differentiation happened, how fast cooling occurred, and which regions of the solar system formed solids first.
Modern threats, Earth's active target zone. So that's the past. What about now? Asteroids haven't stopped flying through the solar system. In fact, Earth is hit every day. Most small, harmless stuff, but occasionally something bigger comes along.
There are over 30,000 known near-Earth asteroids. Those, nearly 900, are over a kilometer wide, big enough to cause a global disaster. Fortunately, we've found most of the largest ones.
But there are tens of thousands of smaller asteroids still untracked. City killers in the 100 to 500 meter range. These don't need to be extinction events to be catastrophic. The 1908 Tunguska impact leveled over 2,000 square kilometers of forest. And that was only 60 meters wide.
That's why impact modeling is so important. Scientists use hydrocode simulations, numerical methods that solve fluid dynamic equations under extreme pressure to predict crater size, airburst zones, and shockwave propagations. These simulations tell us how much warning time we need, what kind of deflection works, and which cities are in danger.
NASA's DART mission proved that we can redirect an asteroid. But detecting them early is key. Right now, telescopes like Pan-STARRS and upcoming observatories like the Vera Rubin Telescope are scanning the sky to identify unknown threats.
And we're getting better at this. New algorithms can predict not just orbits, but impact probabilities decades in advance. Some agencies are even building early warning systems using AI to track objects that could enter Earth's atmosphere in days or hours.
Why? It all matters.
Asteroid defense isn't science fiction. It's planetary insurance. The same physics that explains craters on the moon are the same tools that will protect Earth.
So next time you look up at a cratered moon, remember, those marks are more than scars. They're the fingerprints of the solar system's most extreme sculptors.
and it's still out there.